So remember, we said that sets are one of the nicest things to work with mathematically. We've been working with sets for a long time. We say it's just nice because you can say it's the collection of objects that's going to form a set. So I could have the collection of letters or numbers or elements or whatever. I could take a collection of also sets, right? I could form say a set that consists of the set containing 1 and the empty set and the set containing 1 and the empty set and all of this. You can form these sets. This is really nice. And mathematics is based off of this idea of sets. Right, we saw functions can be defined as sets, relations can be defined as sets. Sets is going to motivate all of mathematics. So at the end of this last video, we were talking about the idea of cardinality of sets. How big are these? What is the size of these? And we asked, is cardinality a recurrence relation or an equivalence relation? So we asked, is it reflexive, symmetric, transitive? And if it is, then it has to be defined on a set. So if you go back to what we talked about equivalence relations or just any relation, it's always defined on a set. So we said if it is defined on a set, that would be the set of all sets. So basically form a collection of all of the possible sets, and that would be the set that we're working with. So that's what we said here. So if cardinality is an equivalence relation, it must be defined on the set of all sets. Okay, so let's talk about this set of all sets. What does this mean? How do we work with this? So I'm going to let S denote the set of all sets. So it's the collection. Basically, you can imagine it kind of like being this box that holds all these other sets in it. Is S an element of the set? So is the set of all sets, is that an element of the set of all sets? Well, it's a set, right? So obviously, yes. Obviously, right? Because it's a set. So every set has to be contained in the set of all sets. So what this says then is that S is non-empty. So S is non-empty. So there's something here. There has to be at least some type of something in here. So we're not trying to prove things about the empty set. If we're proving things with the empty set, then whatever, we don't care. So it's non-empty. So I'm going to define this other set. I'm going to define this set T. T is going to contain all of the sets from the set of all sets such that it's the sets that aren't an element of itself. So for example here, say the set containing 1, 2. This is not contained in itself, right? So this is not an element of the set containing 1, 2. Right, so it's not an element. So we're looking at these types of sets that is not an element of itself. Okay. Is T an element in this set T? So basically, is T inside the same set? We can ask that question. All right. So we have two cases. Because we said with sets, either something's in the set or it's not in the set. There's this very clear dichotomy, right? That's how we said either an element's in it or it's not in there. So is T an element of itself? So suppose that it is not. So suppose T is not in there. If T is not in the set T, well then by definition here, that would imply that it must be in the set, right? Because T is a set, right? And so it has to be in the set of all sets, so it's in S. But it has this property, so then this implies by definition of T that T is an element of T. Okay, so if we assume that it's not an element, we've just proved that it is an element. So that's not a good idea. So let's instead say, okay, what if it is an element then? So if T is an element of this, then what that means is by definition, if you are in this set, so then by definition of the set, so if you're in this, then what that means is that you must satisfy this requirement. By definition of the set, we see that T is not an element of T. Okay, so we have two cases. In this case, we assume that it's not an element, and then we prove that it is. That's a contradiction. Here, we instead say, what if it is an element? And then we show that it's not an element. These are the only two possibilities. But because this is non-empty, we're actually working with something here. So it's not a weird empty set. So what we have is we have this weird conundrum. So this is called Russell's paradox. This is one of the most famous paradoxes in mathematics. This idea basically starts to rip apart our understanding of sets. This famous philosopher was like, wait a minute here. When we define sets in the way that we've defined sets as just the collection of objects or the collection of elements, we start to run into some troubles. So what this Russell's paradox shows is that there is no set of all sets. So it's nonsensical to even talk about the set of all sets. We've just shown that if you do, you just get contradictions. Nothing makes sense. So there is no set of all sets. So what that means then is that cardinality is not an equivalence relation. So because we don't have a set of all sets, we can't define an equivalence relation on the collection of all of the sets. So we do not have an equivalence relation from cardinality. So even though it looked like it was, it is not a relation there. So Russell's paradox, again, watch some videos if you want to see more information about it, read something about it, super fascinating, and we will continue to dive more into the world of sets and cardinalities and hopefully uncover more what type of moments.